Okay, so, the second paper is about verification, and the speaker is Fang-Yi.
Hello, can you hear me? Okay, so hi, I'm Fang-Yi, and I'm the presenter today. And I'm going to talk about how we define a new automata to efficiently verify quantum circuits. And for the outline, we will start from a quantum state and its representation, and then introduce AutoQL framework, and then the new defined level-synchronized tree automata, LSTA, and conclude with the summary and some future directions. And really similar to the previous talk. So in quantum computing, the basic unit is a qubit. And a qubit can be 0 and 1 at the same time. So we usually represent a quantum state as a linear combination of the classical 0 and 1. And below are two common representations for quantum states. For the vector representation, a quantum state is expressed by a column vector. And for the tree representation, as you can see, the left node is correspond to the state 0, and the right node is correspond to the state 1. So now, if there are two qubits in your system, so there will be 4 possible classical states, and a quantum state can be all 4 of them at the same time. So as you can see, the length of the vectors doubles, and you need an additional level for tree representation. So now, if there are n qubits in your system, a quantum state actually encodes 2 to the power of n, that is exponentially many classical states simultaneously. So that is the reason why quantum computing is potentially faster or more powerful than classical computing. And for the following slides, we will use tree representation. Now let me introduce AutoQL framework, a Hall-style automata-based quantum verification framework. So as usual, a Hall triple consists of a precondition, a quantum circuit that we want to verify, and a post-condition. And in AutoQ, the pre-post conditions are sets of quantum states. And a quantum circuit is a series of quantum gates. And so executing the quantum circuit is sequentially apply the quantum gate to corresponding qubits. And there may be a quantum gate that apply to multiple qubits at the same time. So in AutoQ, a Hall triple is valid if for every quantum state in the precondition, after executing, the circuit reaches some state in the post-condition. So now you may wonder why we choose a set of quantum states as our pre-post conditions. So the intuition here is a quantum state is a linear map. So you can verify a quantum circuit by sending a basis of the domain X under it and examine the result. So you can check that if this quantum circuit is actually correspond to a certain linear map. And since a normalized basis is a set of unit length vectors, so it's actually a set of quantum states. So this is the intuition. So the next question is, how do we encode a set of quantum states? Recall that in automata theory, an automaton recognizes a set of strings. So here our goal is to encode a set of quantum states in tree representation, that is a set of tree. A set of trees. So we can actually use a tree. We can actually use tree automata to encode sets of quantum states. That is, given a set of quantum states that we want to encode, we want to construct an automaton A such that the language recognized by this automaton is equals to this set of quantum states. Next, we want to calculate the set of quantum states after executing the circuit. So since executing the quantum circuit is actually sequentially apply all of the quantum gates, we design algorithm for all common quantum gates. So that given an tree automaton A as input, the algorithm will try to construct a new tree automaton gate of A such that this automaton gate of A actually accepts all the quantum state after applying the corresponding quantum gate operation. And for the complexity, the size of the automata increase quadratic or constant to the size of the input automata. And this is for all of the quantum gates except Hadamard. And for Hadamard, it will be exponential, and we will talk about Hadamard gate later. And for the last step, to verify a whole triple, we want to make sure that for every quantum state in the precondition reaches some state after executing the circuit. So this is actually equivalent to check that the set of quantum state is to check if the set of quantum state after executing the circuit is a subset of the post condition. And since here we use automata to encode sets of quantum states, so those sets are equivalent to the languages recognized by some automata. So that is, to verify a whole triple in our framework, it actually reduced to the language inclusion check of tree automata. So overall, as long as we can use tree automata to encode our pre-post condition, and since we design all the algorithm for all the quantum gates, and with the help of language inclusion check of tree automata, our framework AutoQ is fully automated. So I mentioned earlier that the complexity of Hadamard gate is exponential, and this is really bad because Hadamard gate actually occurs frequently in our benchmarks, and sometimes over 90% in some cases. And I will show you that the solution to this problem is our new defined level-synchronized tree automata, LSTA. So first, we're going to talk about what does the Hadamard gate do to a quantum state and why is it difficult for a tree automata to handle it. So given an input quantum state as the tree on the left-hand side, after we apply Hadamard gate on the first qubit, the output quantum state would be the tree on the right-hand side. And where you can see that the left subtree here, the left subtree of the output combines the sum of the left and right subtree from the input. And similarly, the right subtree of the output represents the difference of the left and right input subtrees. So that is, for this node A, when we try to calculate the result of after applying Hadamard gate, node C needs some information from node A needs some information from node C. So in a sense, what we want to try to build a connection between nodes so that we can calculate the result after applying Hadamard gate efficiently. Now, however, in automaton level, that means you try to synchronize between node A and node C. And so one way to, or maybe the only way to do this is you try to propagate the information of node A through the transition and state of automata. So you can imagine that you actually try to pass the information of A through this path. And the bad news is there are exponentially many different branches need to be synchronized as the levels of tree increase. So this is the reason why standard tree automata are inefficient to use for handling the Hadamard gate. So right now, we kind of want a tree automata that can synchronize between different branches efficiently. So since there isn't one, we define it ourselves. So let me introduce once again our level-synchronized tree automata, LSTA. And the biggest difference between standard TA and LSTA is consider that this is a non-deterministic top-down tree automata. So there might be some state queue that have multiple outgoing transition. But in LSTA, you have to label those transitions with disjoint choices. Also, for an accepting run of LSTA, we have this further restriction that if different branches start from the same state at the same level, they must make the same choice. So I will demonstrate this idea with this partial run. And as you can see, both the left and right node are at the same state. So there will be 4 possible following run for this partial run. And since we have the restriction that different branches start from the same state at the same level must make the same choice. So these 2 partial runs are actually illegal. And as you can see, the result is we perfectly synchronize different branches for every single run. So I won't go into detail, but with the help of LSTA, we essentially improve the complexity of Hadamard gate from exponential to quadratic. And here is the verification time comparison between standard TA and LSTA. And the difference is obvious. As you can see, for some cases that is timeout for standard TA, LSTA verify the circuits within a second. And we can also, for the 4th row, we can also verify some interesting properties that after executing one iteration of Grover's circuit, the probability that you get the correct answer increase and up to 200 qubits and within 18 seconds. And you can find more benchmarks results and some comparisons with other state-of-the-art verification tools in our paper. So here I list some key properties of LSTA. So it is closed under union and intersection, not closed under complement. And the emptiness is p-space complete. And we designed the algorithm for language inclusion check. And the problem itself is p-space hard and in exp space. And for the succinctness, there exists some set of tree such that you can express it in linear size of LSTA, but you must use exponential size in the tree automata. And finally, maybe the most important one, LSTA is the expressiveness of LSTA is actually incomparable to TA. And you can find all the detailed proofs and the algorithm in our paper. So for the takeaways, we propose a Hall-style quantum verification framework and using sets of quantum states as pre-post condition, and using tree automata to encode set of quantum states with providing the algorithm for gate operation and the inclusion check for a language inclusion check of tree automata. Our framework is fully automated. And we also introduce LSTA to efficiently handle the frequently occurring Hadamard gate in quantum circuits. More specific, we improve the complexity of the algorithm from exponential to quadratic. And the last point, LSTA is incomparable to TA, and the emptiness and the language inclusion check for LSTA are decidable. The intersection of automata and quantum is a fruitful area of research. And while we continue to enhance the capabilities of AutoQ, our focus extends to a variety of exciting projects. And for instance, we are exploring the use of automata to verify Hamiltonian simulation, a significant application in the field of physics. And also, we try to use automata to automate other verification frameworks, such as quantum hole logic. And this is me, and I'm a research assistant from Taiwan, and I'm looking for PhD position, and I'm ready for a QA, and thanks for your listening.
All right. Questions? Please, over here.
Oh, thank you for great talk. I'm wondering whether can we support intermediate measurement in your framework, because some are promising quantum applications in future, like fault-tolerant quantum computing. Such intermediate measurement is an essential tool to implement quantum algorithms in a fault-tolerant way. How about it?
Do you mean, can we support measurement in our framework?
Yes.
Yeah, and let me expand on his question a little bit. Can you support measurement in the middle of the circuit, or can you only support measurement at the end of the circuit, or not at all?
Yes.
Okay.
We do have an extension for that, but it's an ongoing project. Yeah.
Okay,
So not in the paper?
Yeah.
Okay.
Very
good.
Okay. Yeah.
So I hear from the co-author over here that there's already a paper accepted in TACAS, I understand, that has some of this stuff in it that you're asking for. All right, other questions? Over here.
In our logic, you have two kinds. One that partial correctness or non-terminating execution are ignored, and the one which is total correctness, where you prove there are no infinite executions. So I think you use partial correctness. That is, you assume that execution terminate or not. So I have a related question, which is your tree seems to be regular tree, and so they are built out of finitely many patterns. And if it does not terminate, you might have infinitely many patterns. So I have the impression that it only works if it terminates. Sure.
So, do you mean that if there's a loop in the tree automata, right? So actually, here we do try to use tree automata to construct like parameterized circuit, so we can verify the circuit for n qubit and for the natural number, but it's also an ongoing project.
Okay, I think people are hitting on some good points here. Another question, please? Let me ask you a question. For Grover's algorithm, you had different measurements. What is the property you are verifying for Grover's algorithm?
So for this one, the precondition is only single quantum state. So it will be like so the amplitude for the correct answer will be V high, and the other will be V low. And we tried, and after executing the circuit, the new amplitude corresponds to the correct answer should be like V high prime, and we want to make sure that V high prime is greater than V.
I see. And you can specify that in your framework.
Yes.
Oh, very good. Okay. Who wants to ask the last question of the session? I don't see any questions. Okay. Thank you again.
Thank you.